Along with the question, will something dissolve in water or not, or whatever it dissolves in or not, goes the question, how much will dissolve in water? It's not infinite. Can you dissolve an infinite amount of salt in water? Sugar in water? No. Alcohol in water? Actually, yeah, it's a long story. But we look at the question, how much, and we say X amount. When we reach that amount, we say the solution is saturated, when the water can no longer dissolve any more of that solute. We say it's saturated, it can't hold anymore. Or if, for example, well, let me say I try to dissolve 5 pounds of sugar in a liter of water. You know what, it won't all dissolve. A lot of it will, but not all of it. The water becomes saturated with sugar and can't dissolve anymore. Conversely, we could say take a tablespoon of sugar, dissolve it in a gallon of water. A tablespoon of sugar will certainly dissolve in a gallon of water. We say that sugar water is unsaturated because it can still dissolve more sugar. Sometimes we can actually supersaturate the solution by heating the solvent up on the stove, and as it gets warm, it'll usually dissolve more of the solute. Sugar water can become supersaturated by heating the water on the stove or on a Bunsen burner in the chemistry lab and dissolving more and more and more sugar to the point where at some point we stop heating and dissolving and let it cool off. And as the sugar water cools off, it for at least a little while will hold more sugar in solution than it normally would have at that particular cooler temperature. I'll show you a demonstration in class. Have you ever made rock candy? Or do you know how it's made? That's how it's made. You place a stick or a string into some supersaturated sugar water solution and let it set for a while and watch the crystals of sugar deposit themselves on the popsicle stick or the string. Alright, so we can actually assign numbers. For some reason, the solubility of the salt is usually described in grams of salt per 100 milliliters of water. 100 grams of water. You can change it to anything you want, but it's kind of a convenient ballpark scale for many salts in water. Also, does it make sense to say that most salts dissolve better in warm water? So if I have 80-degree water, it will dissolve more potassium chlorate than 20-degree water. Or if I have 50-degree water, it will dissolve more potassium nitrate than 10-degree water. Or if I have 60-degree Celsius water, it will dissolve more lead nitrate than, say, 5-degree temperature water. Alright, but some are weird. Sodium sulfate, for example. And I'm not in this light blue line. I'm not quite so sure this is absolutely correct, but there are some salts for sure that dissolve not as well in warm water. And I'll let you think about why that could possibly be. Curious. So we can ask all kinds of questions. This is an old clicker question. What's the solubility of potassium nitrate in 100 milliliters of water at 50 degrees? So 50 degrees is right there. And I follow it up to the potassium nitrate line. 50 degrees, looks like about 86 or 7 grams. If I follow it over to the left, 86, 87 grams of KNO3 will dissolve in 50 degree temperature water, 100 milliliters of it. But nothing more than that. So if I had, let's say 90 grams of potassium nitrate and trying to dissolve that in 100 grams of water at 50 degrees Celsius, it wouldn't quite all fit. There'd be about 2 or 3 grams of KNO3 sitting on the bottom of the beaker undissolved, or we could stir it and shake it and suspend it temporarily, but not all that solid salt would dissolve. On the other hand, if I had only 50 grams of KNO3 in 100 milliliters of 50 degrees Celsius water, then it would all dissolve. So another way to say it is, if my point falls below and or to the right of the curve, it will all dissolve its unsaturated solution But if my point of temperature mass of salt falls in the upper and or left quadrant of the curve, above the curve, then all that salt will not dissolve in the water. Some of it will, but not all of it. What if I had 60 grams of KNO3 in 20-degree temperature water, about room temperature water? Well, the answer is no. Not all of it would dissolve. It looks like about 30 grams would dissolve, but 30 more grams would be undissolved and sitting in the bottom of the beaker or something like that. Curious. Do you see how to read this? You got to kind of hone in on the salt you're curious about and ask yourself, well, is the water warm enough to dissolve all that? 30 grams of potassium chlorate mixed 100 grams of water, 3 degrees Celsius. What mass of KClO3 remains undissolved in the bottom of the solution? So I guess not all of it will dissolve. Where's KClO3? Potassium chlorate, oh, there it is. And I'm talking about 30 grams, KClO3. I'm talking about 30-degree temperature water. So 30 degrees and 30 grams of KClO3. So I'm talking about from here to here, that's about 10 or 20 grams of KClO3 of the 20 grams of the 30 grams of KClO3 would not dissolve. Only 10 grams of KClO3 dissolves in 100 milliliters of 30 degrees Celsius water. So 10 would dissolve and 20 wouldn't dissolve in that particular mixture in 30-degree temperature water, 100 milliliters of it. Whoa, what's the molar mass? Well, molal concentration. Yeah, this presumes you've studied molality. I know molarity pretty well. Molality is the moles of solute in kilograms of solution. No. In kilograms of solvent that did the dissolving. So what? Sodium sulfate, 40 degrees Celsius. What's the molal concentration of a saturated solution? Where's sodium sulfate? Oh, it's right here. Yeah, the light blue line I was talking about. 40 degree temperature, 100 milliliters of water. Looks like it can hold 60 grams. 60 grams of sodium sulfate dissolve in 40 degrees Celsius water if I have 100 milliliters of it. That's what this says, over 100 grams of water, 100 milliliters. So let's do a little calculation, shall we? What did I say? 60 grams. Oh yeah, 60 grams fit in 100 grams of water. So 60 grams of sodium sulfate changed to moles. That's why they gave you the molar mass. And the mass of solvent in kilograms that did the dissolving, 0.1 kilograms. Answer, 4.2 molal. And it wouldn't be quite the same molarity because I don't really know the total volume of the solution. Interesting. In class I'll make sure to show you an animation because it's interesting to think about how it is that solutions form, or maybe I've already shown it to you. But in any case, the positive, negative, plus minus traction of the ions that form a crystalline lattice and have associated with that some kind of lattice energy. That has to be overcome by the water molecules, attraction for the positive, negative. And so when something dissolves, we think about the water really pulling the ions apart. Or if something doesn't dissolve, we think about the water attraction not being strong enough. So I guess the water's been left out of this picture so we can simplify. But if we say silver chloride doesn't dissolve in water, what do we mean? That absolutely, positively no silver ions and no chloride ions make it into the solution? And the answer is no. That's a bit of a fib. So when we say memorize your solubility rules, we mean think about things that don't dissolve much versus things that dissolve really well. So most chloride salts dissolve in the water, but silver chloride is one exception. Silver, mercury, and lead chloride don't dissolve very well. So we usually say they don't dissolve in water, but the truth of the matter is that means 99% of them, or 99.999% of them, don't dissolve in the water, but 1 out of 100 or 1 out of 1,000 or a million might, and there's a number that goes with this called a KSP constant. We'll get to that in a later chapter. Most of them don't dissolve, but a few of them might. So really it's an equilibrium. Alright, that's enough for now. My goodness, your brains are full. Go have a refreshing beverage or something. Thanks for studying hard, guys. See you in class.